So we'll wait for a few minutes.
Okay. Okay, Topon, you can start.
Yeah, right, sir. So, good morning to all participants and good afternoon to Datta Madam, Dr. Rukmi Datta. So, today is the 7th lecture session of GIAN course, of this GIAN course on Advanced Permanent Magnet Machine Drive Technologies for Transport, Electrification and Renewable Energy. So, this is the 7th lecture series. So according to our IST, it is almost 10:30, and in Australia, as per my knowledge, it is almost 4 p.m. So it's very close to evening. So I'd like to welcome all the participants, and I'd like to request Dr. Datta to start her session. So on this advanced permanent magnet machine drive technologies. Dr. Datta.
Thank you, Dr. Topan Pradhan. Should we wait a little bit more? Looks like we have only 19 participants, but yesterday we have 30, about 31 students.
Yeah, we can start, madam, a little bit. In the meantime, let me speak a little bit about madam. I mean, you are already acquainted with Dr. Datta, but still, let me tell you a brief about Dr. Datta. So, Dr. Datta actually completed her graduation from Assam Engineering College, and after that, she joined many companies in Japan and in Australia. So finally, she completed her PhD from UNSW, University of New South Wales, and she also worked there as an associate lecturer. And presently, she is working as an associate professor, and she is associated to the research group of energy system, and that belongs to School of Electrical Engineering and Communication. So she has a vast experience of research in this field. She is also associate editor of so many, reputed journals. So if you have any questions related to this topic, so you are always, welcome with your questions and your queries or doubts. So I hope you'll enjoy the lecture. So, madam, I think you may continue.
Sure, thanks. I think you have to give me the host status to share my screen. Could you give me that?
Sure, madam. Sir?
Already, madam, given.
Okay.
Okay.
So we are going to first start with yesterday's quiz, just to remind ourselves what we have done and how you have done in the quiz. First, one of the question was, what was the difficult concept? And it appears some of you have said machines. So hopefully today we will be able to clarify or help you to make it a little bit easier to understand machine again, from following up from yesterday's content. Then there was some few questions. One was about whether surface type PM machine have reluctance torque or not, as a true false question, and majority of you said it is a true statement. That means surface type PM machine doesn't have reluctance torque, and that's correct. Then the next question was asking you to calculate a speed of a 4-pole synchronous machine. So all of you got it correct. So that's great. That means everyone has at least quite familiar now with the synchronous speed concept and how to calculate it. Then the third question was again a true false type. And it said whether synchronous inductance of a PM machine includes self and mutual inductance. So concept of synchronous inductance that we discussed with synchronous machine also valid for permanent magnet machine, and it does include self and mutual inductance. In fact, because of that, the synchronous inductance of a PM machine is 1.5 times of its self-inductance, because we include the mutual inductance in it. So majority of you have got this question correct, 22 people out of 32. Then the next one was to achieve maximum torque in a synchronous machine, we must keep load or torque angle, which is the delta angle, must kept at 30 degrees. So this looks like a split. Some of you said it's true and other half said false. Actually, the answer is false, because the question says any type of synchronous machine, if you noted. So we can get maximum torque with 90-degree delta angle only in uniform air gap synchronous machine, but in salient pole type synchronous machine, that angle is lower than 90 degrees. So that's why that should be a false statement. Okay, so answer should have been false. Then the other one was we discussed a little bit about the magnet material, and then the rare earth magnet material such as neodymium, iron, boron is expensive, and it could also have sometimes issues with the the supply issue, because it is dominantly available only in China. So if we start using this PM machine everywhere, the rare earth material could be like oil of current age in the future. And so that's why we do not want to rely on only one single country for the supply of rare earth material. And that's why there was the look for alternative. So one very obvious alternative could be ferrite magnet, which is cheap, and easily available everywhere. But then what are the problem with it? So that was the question. So if we use ferrite magnet, main problem will be because it has low energy density. So machine size will be much bigger. And it could also demagnetize easily. Low efficiency it could be avoided because we still do not have high losses from the rotor, but because magnet is now providing less magnetic flux, so current need to increase. So because of that, copper loss can increase. So that may bring the efficiency low. So those were the three key disadvantages if we want to use ferrite magnet. And the last two questions were basically two simple numerical questions that was based on Dr. Clay Chu's tutorial, and it appears in both those questions, majority of you have got correct answers. So I congratulate you. And hopefully today also we will have a very fruitful tutorial as well as lectures. So now let's go to the lecture component of today's part. Okay, so let me start with today. We are third day of our course material, and this is the second part of the permanent magnet machine, where we will be discussing mostly how to design it today. Okay, so we'll start with some fundamental definition. Then we'll go to the analytically how to calculate some of the main dimensions. And then we will go to the more detailed about how to do it using finite element modeling. So in the tutorial, which will be like a finite element workshop, you will be able to maybe even use some of the concept that you learn today's lecture.
Madam,
Okay?
Madam, can I interrupt for just 1 minute?
Sure.
So, Madam, at the bottom, you please see whether recording is going on or not.
Okay.
The two lines are. This recording, I think, going on.
I cannot see the recording.
Yeah. Recording is going on, sir. I can see. Recording is going on.
Okay. Okay.
Okay.
Oh, all right. Okay.
Okay.
So moving ahead today, what are our learning goals? So in the first section, you will identify the fundamental parameters related to AC machine design. Then we will learn how to select main dimensions using a very well-known equation known as sizing equation for machines. And then you will also be able to get some interpretation of theoretical aspect of a finite element based machine design. And later, hopefully in the tutorial, you will be able to design analyze the PMSM using both analytical tool and finite element. So let's start with looking at a surface type PM machine. So in our right hand side, you can see the rotor here. Let me just probably bring the ledger pointer. So you can see the rotor here. That's the magnet piece. These are the magnet piece glued on the rotor. And this is the stator, okay, where the windings will be inserted. So this machine, in fact, we can model using 3D CADs. So that your left-hand side figure, the 3D figure, is a CAD drawing. In fact, in finite element analysis, we can have a CAD drawing like this and then do FE analysis. Or we can do a 2D model. So here you are seeing again a permanent magnet machine top view, but this is the interior type one. So if you look closely again, you'll see the stator slots, the magnets in the rotor, and the shaft. So this is the geometry which we need to build in the finite element. But to build this, we need to know the dimensions, okay, of each and every component. So when you want to start designing a machine, so that's why the first step is to find the main dimensions. And only after that, we can do anything else. So always, the first step is actually analytical calculation of the main dimensions, which give you a very basic machine. And you may use further analytical equations to calculate some performance, or you can just directly go to the finite element and start finding more accurate or predicted performances. Now, to build this geometry, as we said, we need to know if some of the fundamental quantities, and need to be very clear about that. So first we will be going to look at those, and then we'll move to the sizing equation. So as I said, the geometry, so we have to define the stator. We have to draw these slots where the winding will go. If it's a surface type, this geometry is shown for a surface type. So we will need to know what's the width of the magnet, what will be the radius up to the magnet. We also have to define the length of the air gap, shape of the slots. So this is like a top is flat. Sometimes you will see that in the previous figure, you have seen the slot with a arc shape. So the different type of slots. So what type of slot that can also be decided beforehand. Now, after knowing what the geometry is going to be, we also now need to be very clear about that how pole numbers, okay, how many poles we're going to have. So we could use in our various definitions the total pole number, or we can use pole pairs. So just be careful. Some equations uses, or some calculation uses pole numbers, and some others uses pole pairs. So to be, if we do not use the correct one, we will end up having double the number of whatever we are calculating. So that's why always pay attention whether the equation is talking about pole pair or pole numbers. And then the other one is electrical speed and mechanical speed. Some of the, again, in some of the equations, the electrical speed is used, especially the equations where we talk about the controls. Whereas in the defining geometry, such as this one, the angular thetas, the positions, can be found from or can have a relation to the speed at which the rotor is rotating physically. That means that's the mechanical speed as well as mechanical angle. We know that we have 360-degree total mechanical angle, but based on our pole numbers or pole pairs, the electrical angle could be more than 360-degree, as you know, because electrical angle is mechanical angle time the pole pairs. So if we have a more than one pole pair machine, the electrical angle and mechanical angle is going to be different. Similarly, electrical speed and mechanical speed going to be different. So again, we should pay attention to which speed, which angle it is referring to in those analytical calculations. So, and then the windings. So we have talked a lot about windings. It's very important to be clear about what this winding actually means. And what is conductor? Sometimes you will see that it refers to conductor. So what's the conductor and what's the difference between a conductor and a winding and a coil? You can see from this picture. I like this one, this very simple picture. So remember that we need at least two conductors to form one single turn. Okay, so if it says number of turns in a machine is, let's say, 20, that means we have 40 conductors in that machine. So always 2 times of turns is the number of conductor in your machine. And then most of the time we have more than 1 turn in our coils. So a coil is something in which you have more than 1 turn. And then winding is actually many coils connected in series or in parallel, depending on the requirement of the machine. So here you can see how windings are being fitted to the slots. Okay, this is for specially designed machines or even for conventional machines. This actually is quite a interesting thing to look at. They are not very difficult to understand, but and when anyone can, with good experience, can actually own the machine. But the phase, we have to have 3 phases and coils related to all those 3 phases. And they have to be located at 120 degrees. So there is a process how to insert these coils or windings, and otherwise we will end up machine with unbalanced winding, or and then the performance just will not be what we are expecting. So winding is actually, although it's considered to be simple, but it is one of the important things for a machine. And then in the our machine, a few more things we need to be aware of. One is that the pole pitch, which is like just the peripheral distance between 2 identical points of 2 adjacent poles, as you can see from here. What does pole pitch mean? And how do we calculate pole pitch? We can simply divide the total 360-degree mechanical by number of poles. Very easy. Okay. However, that's how we find pole pitch in our conventional synchronous machine or in our induction machine. However, in PM machine, there's a little bit of difference. It may feel like that the magnet should be the pole pitch, right? But if you look at this again, a surface type machines, 1 pole we are seeing here. So pole pitch is defined from midpoint of the interpole of one side to the midpoint of the interpole of the other side. That's the pole pitch. And your magnet may not, magnet's arc or the length or width rather, the width may not be same as pole pitch. Often it is not, because if you remember our previous figure of a surface type PM machine, there is a small gap between each piece of magnet. So that's the interpolar part, okay? And we don't have to make the magnet as wide as the pole pitch. And having this interpolar region is actually useful if we put the magnet next to each other. Magnet, then if this is a north pole and next one is the south pole, all the flux will try to just go to from one magnet to other piece, instead of crossing the air gap, going to the stator and coming back. So that there will be lots of leakage just between, or sorting of the two magnets, short circuiting between two magnets. You can think like this way. So we could prevent that by having that small gap between the magnets. So this is a requirement, especially for IPM machine. You must have that gap, and this is known as actually the flux barrier. So we can just quickly go back to the PM machine. So you can see there, that part is usually non-magnetic, that's a triangular set part. And then there is also iron in between. So that triangular set part is called flux barrier. And we have that flux barrier to prevent short circuiting between the magnets in IPM machine. So is also in SPM machine. So there is a gap here. So that's why pole arc pitch and magnet arc are not same in PM machines. And then the coil of a in your stator. So what's the width of your coil? That's the coil span. If the width of the coil and the pole pitch are same, then we say that we have a full pitch coil. But sometimes having the pitch shortened is actually useful. By making it shorter, we can reduce certain harmonics in the magnetomotive force and also in the EMF. If you remember from our last lecture, magnetomotive force was, or MMF was a staircase type waveform, and it has harmonics. And you do not want certain harmonics, such as mostly the odd harmonics. You want some of the odd harmonics can result in vibration and also can result in noise. So those harmonics can be eliminated using short pitching. Of course, also using narrower coil, we can reduce copper uses as well. So that's why there is advantage of short pitch coil, and it's often used for all type of conventional three-phase machines, including PMSM. So when we have a short pitch winding or short pitch coil, that effect need to be included in our number of turns per phase, and that is actually defined from the by a factor called pitch factor. And this pitch factors, the basic definition is that it is the ratio of the induced EMF in the coil of a short pitch coil as your numerator, and the EMF of a full pitch coil. So if we take the ratio of these two EMF, it gives us a fraction, and that's the pitch factor. So pitch factor is always less than 1, but we may not know the EMF before we build the machine. So instead, we can actually analytically calculate it using a formula. This is a fundamental formula. You can find it in any electric machines book, especially the first one. So we can calculate pitch factor for different harmonics of the MMF. So if it is for the fundamental, then the H will be equal to 1. So the fundamental MMF. And it is the cosine function of the angle. So what is this angle? This angle is, this angle gamma is actually known as slot pitch angle. So what's slot pitch angle? Again, it's a very simple concept. How many slots you have in your machine, and you divide the total 360-degree mechanical by the total slots, and you get your slot pitch. So we can shorten the coil by one slot. So that from there, actually, this pitch factor becomes function of the slot pitch angle. So we can find it if we know the slot pitch angle straight away, or if we can, and we can take help of it, and then we can define what should be the width of the coil. Okay, what should be the width of our coil, and what if we know what is our pole pitch. Okay, so there is a relation between the pole pitch, width of the coil, and the pitch factor, in fact. So that's what this equation shows. The next factor, which is again quite well known in the classical electric machine textbook, you will find it. That's the distribution factor. The distribution factor comes from the fact that all our coils are distributed over number of slots, as you can see here. So this shows us the two sides of a coil, and all these could belong to one phase, and the others could belong to the other phase. So we could have many number of coils, as I said, and these coils could be connected in series or in parallel. Is there any question?
Hello, is there any question from your side? You please write it down. Let Madam finish. Then you can start.
Okay, sir.
Yeah, hello.
Maybe there is just background noise. It could be just background noise. Sorry?
Yeah, I think he forgot to mute. So, Madam, please continue.
Okay. All right. So I have seen that Himanshu has a question, and I'll answer that question in a minute. But let me first complete what about the windings first. Okay. So that winding had, so that distribution effect is included by the distribution factor. Again, it actually comes from the ratio of the EMF. Since we have more than one coil, so sum of the EMF in each coil, we can get it as an arithmetic sum, or we can get it as a phasor sum of those EMF. So the ratio of those two sum of EMF actually the distribution factor. But again, as I said previously, we may not know the EMF when we are designing it. So instead of using EMF, we can take help of analytical equations such as this one, 3.2, and it's a sine function, and also it consists of, again, the slot pitch angle gamma. H is the harmonic number. So if we are doing it for the fundamental component, H is going to be 1. And we also need to know how many slots are there per pole. So this could be calculated very easily. If you know total number of slots in your machine, divided by the total number of pole, you will find the Q, slot per pole, and this can be easily calculated out. Again, this is always less than 1. So we have two factors from the winding, pitch factor and distribution factor. And then how are we going to put these windings in the slots? Based on that, we have two types of windings, one double and single layer. Concept is very easy to understand. If in our slot, we only have one coil side, that means one side of your coils as you or that this could be that is number of conductors if we have more than one turn. If it is one turn, then it will be one single conductor. Okay, so in this picture it is shown like a as if only one conductor, but this could consist of number of conductors. Okay, just for simplification it was shown like this. So single layer means we only have one coil side in the slot, in each slot, and in the double layer we could have two coil sides, top and bottom. So that's why the name double layer. What's the advantage of single layer is that since they are quite physically separated, these coils are, so that they have the mutual inductance is usually smaller. In fact, the winding that we discussed in our last lecture, that's the concentrated type winding. In concentrated type winding, if we use single layer structure, then the mutual inductance can be even made 0. So what's the advantage of having low mutual inductance? The fault tolerance, because that means your two phases are electrically nearly isolated. So that gives it a better fault tolerance. But the problem with single layer winding is that you can't, especially in distributed winding, you cannot make it full pitch. So you can only make full pitch. You cannot have short pitch. So single layer winding can only be full pitch. Whereas the double layer is, you can make short pitch as well. But because now two sides of it, two different coils are sitting in the same slot, so you could have much higher mutual inductance. So the fault tolerance will be lower. We can decide if our motor need to be very fault tolerant. For example, if you're designing it for aerospace or very safety critical applications, then maybe having a fault tolerance is your highest priority. And then maybe you can compromise with a full pitch coil. With full pitch coil, you will have some extra harmonics in your ABAP and EMF, but maybe they can be dealt with some other way. Okay, so that there is a trade-off. Which one we want to use, double layer or single layer? And the double layer, when it is used with concentrated winding, it again helps to reduce some of the harmonics. So for concentrated winding, double layer has become quite popular. For conventional machine, distributed winding, if we want short pitch, then it is a double layer winding. But if we want fault tolerance, then we may select single layer full pitch winding. So those are a few fundamental things. Now we are ready to look at the design steps. Okay, so what are we going to, what is the first step for if we want to design a machine? So first will be obviously the application, if we are designing something novel or new. But if we are doing it for conventional applications, then the first question will be, what type of machine are we designing? Is it a synchronous machine, induction machine, reluctance machine, or PMSM or BLDC, what it is? So that's the first question we have to answer. And once we decided what type of machine it's going to be, after that, next we would have to look at whether we want internal pole or external pole. So here the internal pole and external pole doesn't mean SPM and IPM, okay? This is a different concept. Your rotor could sit inside the stator hollow cylinder, or your stator could be inside and rotor could be outside. So if the rotor is outside, that's the external pole configuration. And this type of external pole configuration is could be useful for applications such as like a racing car, in which you put the electric motor actually in the wheel. So your wheel, the shape of the wheel is such that it is favorable for external pole machine, because the whole thing, your rotor could be the wheel rib itself, okay, and then stator could sit in the middle. Also, for the electric bike, there are in that case also, those of you who drive ride on bike, you can probably visualize it, that your wheel rim now becomes the rotor and the stator sits in the center. So that's again favors external pole type construction. Internal pole is the conventional one. Rotor will be sitting in the middle and stator outside. If it's PM machine, we also have to decide whether we want to use axial flux type PM machine or radial flux type at this stage. And then, of course, we need to decide what's the power and speed for that our design machine is going to have. What pole number, what's frequency, voltage, phase? Is it going to be a continuously running motor, or is this application requires the motor to be running only intermediately? So there are some applications where you need to turn on and off your motor frequently. You don't have to keep running the motor continuously. So in that type of case, you could have much high current, because that high current flows only for a small period of time. So temperature increase is less compared to a continuously running motor. So that's why intermediate duty machines could have much higher current compared to a continuous duty motor. And then other things is like enclosure, like what type of enclosure are you going to use? If you're designing the motor for, let's say, the very harsh environment such as the mining, you have to have the motor enclosed by such compact and such like AR type feature, so that no spark, nothing can escape its structure. Okay, because in a mining, if a small sparks comes out, it could be a disaster, right? Also, same thing for refinery. Some pump where they are handling the very flammable liquid, then again, it needs to be very, very robustly enclosed by certain enclosure classes. And after all this, conventionally you come to what should be the efficiency ripple, what should be the maximum torque, what should be the control, etc. And then, of course, you decide your cost and manufacturability, and it must compile with the standard, whether it is Indian standard or whether it is international standard. If you're importing your motor, it must comply with the international standard. Now, these are the conventional design steps. Okay, so it is not application specific exactly, as you can see. But later, a little bit later, you'll see that this design process is now changing because application is making some of the steps a little bit different. So if we are doing for a conventional application, then we should follow these steps. Okay, and some of the things are already will be fixed. For example, the standard will decide what should be the size, frame size of the motor. Or maybe you do not care so much about efficiency, or maybe you don't care about torque ripple, so you do not make them as your objective to increase or increase efficiency or reduce ripple. But that's now changing. These things are becoming more and more important. So that's why the design optimization part comes. So once we have decided what is our motor going to be, next step is to determine the main dimensions. So what are those main dimensions? One of the important one is what is the outer diameter. Okay, so from the center of your motor, that will be your outer diameter. And this outer diameter, if we are designing the motor for standard applications, it will be decided usually by the standard frame sizes. There are different frame sizes, and that will already tell us what is this diameter need to be. And the next one, important one, is this length, axial length of the of your machine. We also need to know what should be the width of the slot. These are the slots, as you can see. What should be the height of the slot? What is going to be the air gap diameter? So air gap diameter means actually the internal diameter or internal radius of your stator. So here, again, you need to know what's this radius or diameter is. And then we decide what should be the air gap length. Okay, so if it is a surface type PM machine, PM height will also come in a series with the air gap. But if it's IPM machine, magnet would have been sitting here. Okay, then the air gap length, the physical air gap length is the effective air gap. And then we also need to decide what is the back iron of the rotor, this part. Okay, and how many poles, what's air gap, frequency. And one very important one is what's going to be the air gap flux density. Okay, so all this need to be decided. So how do I decide it? There comes the concept of the sizing equation. So the first step of a machine design is actually always the sizing equation. So it may look like a very weird, large, complex equation, but we will break it down, and then you will see that it's although it looks very complex, it actually comes from very, very basic understanding of our power and torque. So that the sizing equation, in our left-hand side, we have the output power of the motor, and then some constant here, the efficiency of the motor, frequency, pole pair, phase numbers, diameter, air gap diameter of your motor. So air gap diameter means inner diameter. We can also call it inner diameter of the stator. The length of the motor, what is the air gap flux density, and this letter A actually represents what is the electrical loading. So what's electrical loading means is it's again a quite simple concept. It means how much current per meter in the periphery of your stator. Okay, so if you know your total current, you divide it by the perimeter of your stator air gap diameter, or sorry, the circle that's created by the air gap diameter. Okay, the perimeter of that circle. And so that we can use this equation to find diameter, length, or we can find the electrical loading or magnetic loading if we know what is the power requirement and what is our size. Or we can, if we beforehand decide what is our electric loading and magnetic loading, and we know our power, we can calculate the size. So both way it works. Okay, sometimes the size is already known, or size is constrained by your application. As I mentioned in the first lecture, in electric vehicle, you have only limited space. So that limited space already decide what could be the maximum air gap diameter and length maybe. So in that case, you know this already for the motor, and you know how much power we need. And then we just find out what should be the loading, electric loading and magnetic loading. Sometimes the same equation actually, when we express it as a torque, we divide the power by speed. So when we do use the torque concept, you will notice that we don't need to decide the frequency and pole pairs beforehand, before we design. If we use the torque sizing equation, that for frequency per pole pair has been canceled out when we have divided this equation by the speed. So in this part, again, we have electric loading, magnetic loading, and diameter and length, but we don't need to, we don't have frequency and pole pair in the equation. So if we use torque equation, we don't need to decide beforehand what is frequency and pole pair going to be in our first step. So now let's look at where this sizing equation actually come from. So it starts with the very basic definition of power. So instantaneous power, as you know, is voltage times current. Now, if we consider the input, but that instantaneous power is our input, then the input power to the motor, instantaneous input power to the motor, multiplying it by efficiency, so it gives us the instantaneous output power. But if we take the average of our instantaneous power, then we get the conventional, our power equation in terms of either RMS value or peak value. So from here it starts. The efficiency, phase number in a time period of capital T, we find the average input power. In the input power equation, actually, instead of voltage, the EMF is used. Okay, so here it assumes that resistive drop or any leakage inductive drop in the machine is negligible. So it's neglected. And from there, we get our power equation. And this equation, when it was derived actually in 1998 by Professor Lippo, Tom Lippo, he has only recently passed away, but he was one of the pioneer in the developing this equation. And this paper is available in the IEEE Explore database. So if you are interested, you can always read this paper to understand the Sarzik equation in more details. And it was developed for any type of motor, okay? It's not for PMSM alone. So that's why some of the things, the constants that you have seen actually comes by. So since here we are not assuming the motor to be a three-phase sinusoidal motor, so there is a factor included here, which is referred as the power waveform factor. So power waveform factor is actually, again, quite simple concept. It comes from the ratio of the instantaneous average power over peak power. So if it's a three-phase machine, it's actually your instantaneous average power is RMS, voltage RMS, current RMS time the power factor. So here the power factor, since we are using EMF, so that power factor angle is actually the angle between EMF and current, okay, not voltage, terminal voltage and current, okay. So that's your average power, and peak power is simply the peak value of the voltage and peak value of the current. So if we do the ratio of it, this factor is half time the power factor. So this equation for a three-phase machine, in fact, will become efficiency time 3, because three-phase, Kp is half time cos phi, the power factor, time the peak value of the voltage, the peak value of the current. So it's actually a quite familiar equation, in fact. Now, in this equation, the EMF going to give us, or EMF is related to the air gap flux density that comes from the rotor flux, as we have understood from our yesterday's discussion. And current is coming from your stator winding, which is carrying your stator current. So this current relates to the electrical loading, and EMF relates to the magnetic loading of the machine. So what is the back EMF? Oh, sorry, what is the induced, EMF, peak EMF, and what is the current in terms of flux density and in terms of current density? That will, in fact, translate to the Sarzik equation. So EMF, from Faraday's law, as we know, can be expressed in terms of phase and, number of turns in a phase winding, air gap flux density, frequency, pole pair, and the flux is, as we know, flux density time the area. So that area, actually from the concept of the area comes this two dimensions, the air gap diameter and the length, okay? So because it is stator is a, the cross-sectional area of the air gap can be thought of like a cylinder with curvature surface. So it is, that area is 2 pi r time the length of the cylinder, okay? A cylinder means it is the length of our machine. So from there, these two comes, diameter d and the length L. And since our windings are distributed, so we have to consider the winding factor. And winding factor, as we discussed previously in our yesterday's lecture, it actually, we didn't looked into it at that time, what includes what is inside of the winding factor. Now we'll be able to do that. So if you remember distribution factor, which we defined previously today, and the pitch factor. So those two together, if we multiply, actually is the winding factor. And we could also have a skewing factor if the stator is not, that it's constructed with a skew, okay? So that the skewing is not always common, So if there is no skew in the stator, then skewing factor is simply 1. Otherwise, it also has a empirical formula to calculate skewing factor. Especially in PMSM or PM machines, there is no skewing of the stator most of the time. So that's why I haven't shown you the formula, but if you are interested, you can always find it from the classical textbooks. So winding factor times a 2 pi, factor of 2 pi comes also, because remember it is the Fourier analysis, and this EMF peak value is related to the fundamental. So that 2 pi actually comes from there. So our EMF constant is for a 3-phase machine is winding factor times 2 pi. So that's our EMF, and you can see that EMF is related to the magnetic loading. And then the current. Next one is we have to look at how the current relates to the electrical loading. So as I mentioned previously, this equation is developed for any machine. So that's why they didn't assume what is the relation between peak current and RMS current. They simply assume it is Ki. So if your current is not sinusoidal, then this value of Ki may not be √2. Okay, but in 3-phase conventional machine, this relation Ki should be √2. IRMS is Im over √2, right? So from this current waveform factor, we can find what's the relation between peak current and RMS current. And RMS current divided by the total length around which the winding is gives us the electrical loading. Okay, so IRMS times the number of phase in our machine. If we have only one single stator, sometimes we could have more than one stator in certain machines. So that's why they, again, didn't assume it to be just number of phase to be 3. They said number of phase of each stator. If we have more than one stator, then we will have a value of M1 for each stator. But in conventional PMSM, we only have one stator and we have 3 phase. So this M1 will become actually 3. Number of phase divided by pi times air gap diameter. So this pi d is the perimeter of that circle, right? So dividing the total current of a phase, total current of the 3 phase by the perimeter gives us the current loading. There is a factor of 2 here. This factor of 2 actually coming from because we are using number of turns. But the current loading means total current in a conductor that is wrapped around this circle. Okay, so if you remember, conductor number is always 2 times of the turns. So that's why, because we are using turns, so that's why an additional factor of 2 comes in the equation. So loading is basically total RMS current divided by the perimeter around which the conductor is wound. And should note that the unit is ampere per meter. Okay, so it is a kind of a current density, but it is a line current density. Okay, it's not the current density per meter square. And so that's our stator current loading. But we may have a rotor current loading as well, especially in induction machine or even conventional synchronous machine. Your rotor also has current. So if we consider there is a rotor current loading as well, then the total current loading A should be total current loading of stator should be the total current loading minus the rotor current loading. Okay, and the relation between the rotor current loading and stator current loading is defined by a factor K5. But in a PM machine, we don't have rotor current loading. So total current loading and stator current loading becomes the same thing. And K5 is simply 0 in that case. Okay. K5 becomes 0. So it just becomes AS equal to A in case of PM machine. Okay. So the peak current now we can express in terms of RMS, the current loading, total current loading times the current factor. So we replace our IRMS from the equation from here. So IRMS was in terms of current loading. So we can substitute what IRMS, or we can define what IRMS in terms of current loading from this equation and bring it back to our peak current definition. So peak current definition is current form factor times IRMS, and IRMS replaced by now the current loading, and we can replace the current loading of the stator by the total current loading. So then AS becomes A over 1 plus K5. So this is a general expression for any machines, okay, any electric machines. And so now in our power equation, so we replace our EMF by the one that we have found from the Faraday's law, and we replace our peak current with help of the current loading. Okay, and then now you can see where those constants are coming from. Okay.
Current spring limit. So ikkada S1 minus S2. A symbol in the.
Is there a question?
Do any one of you have question? Hello? If you have any question, please speak up, otherwise mute yourself. I think, sir, madam, there is no question, so you may continue.
Okay, thanks. So that's how our sizing equation actually comes from, okay? And for a PMSM, we can replace all these constant according to the known values. So as I already said, the KE is the 2 pi times winding factor. KP is actually half time power factor angle, cosine, or sorry, cos power factor, that's cosine of the power factor angle. And your KI is √2 for a 3-phase machine. So that equation becomes very, very simple, in fact. And then so is the torque equation. So only thing that will be unknown here is these 4 quantities. And we can, as I mentioned earlier, we can, if we decide 2 of them, other 2 can be found. Sometimes even it is made even simpler by determining what's the ratio between the axial length and the air gap diameter. This could be in some application. This is actually, this ratio is called aspect ratio, and this is already sometimes predetermined. So if that's the case, then in fact our equation becomes the function of only air gap diameter. Okay, so that means only these 2 are unknown, or if this is already determined, then the diameter can be found. Sometimes it is made even easier if we if the ratio between outer diameter and the air gap diameter is known. So then the equation can be expressed using the outer diameter. So that's the sizing equation, but we have to be careful with a few things in the sizing equation. That is the loading actually is decided by the current density that the conductor can carry and how many conductors we can fit into the slots, okay? And it also actually determined by how much temperature increase we can allow here, okay? So there are limitations on what could be your current loading. So you can see as the loading increases, the requirement for cooling the machine also increases, okay? And you can see a few examples of some typical value of current density and current loading used for different horsepower motors in the literature, okay? On the other hand, the magnetic loading, the BG, it also has some limitations. So it is like how much saturation you're going to allow in the machine. Based on that, actually the air gap flux density like need to be limited. You cannot like keep increasing your air gap flux density to a very high value, because if this is very high, if you can do that, it's always of course depends on the magnetic circuit how much air gap flux density you can get, but by somehow if we could make it go to as high as we like, but then that it will make the iron core make saturate. So if iron core saturates, then as we already know that we are there could be a lot of other issues. So that's why the saturation, maximum saturation allowed in the core, magnetic core, are again determined by industry standard. And based on that, we can find out what could be the possible maximum magnetic loading that can be allowed. Other than that, there are a few other things we have to consider. That is the stress, the mechanical stress caused by the magnetic force, known as shear stress. And the shear stress, in fact, proportional to electrical loading and air gap loading. So if we keep increasing our electrical and magnetic loading, this stress will increase, and at a certain point your rotor can break down. So you cannot, that also tells us that we cannot just keep increasing electric loading and air gap loading. And the other one is what is the torque per rotor volume, TRV. So this actually determines how small you can make your rotor, okay? And this, in fact, through this a bit of mathematical expressions, manipulations of the torque equation and the rotor volume, it can be shown that it is the TRV is in fact directly proportional to the shear stress. So if we make the rotor very small, the stress on the rotor could be also very high, and then it can break. So this is a very important things to consider when you are designing high-speed machine. In high-speed machine, your machine could be very, very small. Okay, as you have seen in the sizing equation, that if the frequency increases and your power is kept constant, and these two are fixed, the air gap, electric loading and magnetic loading, then these need to go down. Your air gap diameter or the diameter and the length need to go down. This volume need to go down. So for high-speed machine, that's why usually the rotor and stator both are very small for the same amount of power, and that means the stress on the rotor would be very high. And if we do not give proper consideration, we could build a machine which will break once you start running it. So that's need to be keep in mind. Another thing is that as we increase pole numbers, it can be shown that the depth of the stator yoke actually reduces. Okay, so this is again was found not very long ago that the pole number and this width actually inversely related. Okay, as the pole number increases, this was 2 pole to 8 pole, you can see that this machine has become smaller because that width has become smaller, and that can cause, that could again could be a problem because it is a saturation. It could be a saturation issue. And then we could the winding, how to distribute your phase windings is need to be known. That we always start with a positive side of our winding, and then since the other two phase must be 120 degree physically apart, so that determines where should be the next positive of the second phase and the negative of the third phase. So this is always known, okay, for a 3-phase machine. And based on this, the coils can be distributed in the slot quite easily for each phase. So it's showing how you will decide where the phases will be in your slot. If you are doing, let's say, finite element analysis, you have the geometry. Now you have to assign the phases to the various slots. And that can be found through that quite well-known relation. Other than that, concentrated winding we talk about, you can see how they are different between distributed winding and concentrated winding. And concentrated winding could also have a slot per pole per phase, not integer, could be a fractional number. And we also, once we know the length and cross section of our windings, we can initially calculate out what should be the resistance of our windings. So these are the few things which we can easily calculate analytically, but they are, if we want to do more performance analysis, usually they are not accurate because we are ignoring magnetic saturation, leakage, complex geometry, etc. And we need, in fact, finite element. We'll take maybe a break. I think we have gone nearly 15 minutes over. So let's take a break.
Okay, for how much time? No? 5 minutes break. Okay.
5 minutes
so,
break. Yeah.
all of you can come back after 5 minutes.
Yeah, it is now, I think in India, 11:47. So let's say 11:50. So maybe by 11:55.
55.
Yep, 11:55
Yeah.
is okay.
Yeah. Okay, ma'am. Okay, ma'am.
So we'll
So
come back at
all of
11.
you may just I mean go wherever you wish for 5 minutes and then come back after 5 minutes. I mean Dr. Datta will continue her lecture. Okay, ma'am. No issue. We are there.
Thank you. Thank you.
Thank you, madam.
Thanks.
So, madam, are you there?
Yes, I'm here. Okay.
So I hope the participants are here and some are yet to come back. So I mean, should we start or
Yeah,
we
we
wait
can
for another
start.
1 2 minutes?
Uh,
Yeah. So let us
as
start,
you
madam.
like, as you say. If you want me to wait for a minute,
So
I can.
madam, let us wait for another 1 or 2 minutes because maybe some of them will be joining shortly.
Sure.
So those who are present here, they can just inform the people who are yet to come or yet to join. So as soon as they join, Dr. Datta will start.
Is Himanshu there? Because he has a question. We can discuss that question.
Himanshu is there, who posted the question. Himanshu. Amit is also posted a question, Amit Kumar.
Yeah,
So is
sure.
there anyone out of these two people, Himanshu or Amit? Hello? Himanshu? Oh, Amit is there, madam. So
Okay,
Amit, your question is, yeah, Amit's question is that why skewing factor is not needed in PMSM.
Yep. And what
Then
is
second
the
question is that what is intermediate duty motor?
Yep.
What is the basic concept behind magnetic loading? Yeah, so
Okay.
these are the questions from Amit. So,
Sure.
I mean, madam.
Sure. Okay. So I'll start with Amit, and hopefully by that time Himanshu will also come back. So he has also come back. I think his mic is not working.
Yeah. Himanshu has come back, but his mic is not working. So, I mean, he'll be able to listen to you.
Yes, sure. All right. I'll start with Amit's question. So why screen factor is not needed in PMSM is basically the skewing is used in the induction motor, so to reduce torque ripple. But in PMSM, it's a synchronous machine, and in synchronous machine, the skewing usually the effect of skewing on torque ripple is not as good as in the induction machine. So that's why like it deemed to be not necessary. So that's the main reason why skewing is not very common in PMSM, especially the skewing of the stator or skewing of the windings. Okay. The other question is intermediate duty. So sometimes in industrial applications, you may need to turn the motor only for a short duration and then you turn it off. And maybe again, it repeats. After a certain time, you will again turn it on. And then again, for a short time, it runs and then stops. So that is an intermediate duty motor, okay? It doesn't run continuously. Whereas in some other applications, you have to, for example, let's say the refinery, you are handling some chemicals by a pump, and it need to handle that chemical maybe for 24 hours. In that case, the motor has to run all 24 hours, 7 days a week, and then that's a continuous duty motor. That's the difference. So because in the intermediate, you only need to run the motor only for a short duration and then you stop. So temperature cannot increase to a very high value even when you use a high current. So by the time temperature can go to high value, you already turn it off. So that's why intermediate duty motor can have higher current rating than the continuous one. Now the magnetic loading is because in our motors, the torque comes from the flux density and the current. So that magnetic loading means what's the flux, contribution of the flux, okay? And electric loading means what's the contribution of the current to get the power or get the torque. That's the concept of magnetic loading and electric loading during design. Okay, we want to find a balance. You do not want all the tasks to be done by the current, because if you do that, your copper loss could be much higher. And you also do not want everything to be done by the magnet flux, because then the saturation issue comes. So there need to be a balance between the two. Now going back to, hopefully I have answered. Now I'll go back to Himangshu's question about why the V shape in the IPM machine. So this is actually a quite nice segue from Amit's question of magnetic loading. So when we have the V-shaped, we have the pole pitch of a flat-shaped IPM machine and a V-shaped IPM machine exactly same. But we can put a much longer magnet when we put it in a V-shape. Okay, and what's the advantage? We can push more, that means we can get more magnetic flux out of the same space. So that's the region of advantage of a V-shaped topology compared to the flat-shaped. You can get more flux from the same space of pole pitch. Okay, thanks for the two questions, both of you, Himangshu and Amit. I'm glad that you are finding them interesting. Now let's move to the second part. Yes.
Ma'am, can I listen me?
Sure.
I have one question, ma'am.
Sure, Manoj.
Actually, as you said, that is the pitch factor and distribution factor. We made that in order to reduce the harmonics.
Yep.
And if we see that EMF equation of that machine, and this is also play a major role in order to reduce the induced EMF in the machine. So I want to ask you that in the design prospect, if you do that pitch factor and distribution factor consider, there is a significant amount of reduction in the EMF. So up to what extent we can go for that pitch factor and distribution factor so that there is a balance between the EMF reduction and the harmonic reduction?
Very good question, Manoj. Yes. So yes, so there is always a trade-off actually in the machine design. So if you want to reduce harmonic, and you can end up with a winding factor, total winding factor of 80%, then it's not good, right?
Yes.
We are not getting enough out of it. We are already losing 20%. So that's why the convention is that you do not want to reduce your total winding factor below 90%. Okay, so above 90% is acceptable in the industry. So that's the limit you have to put in. So if you have a pitch factor of 0.8 and distribution factor of 0.8, so that's together you get 0.9, right? So that's your limit. You should not go below that. You can compromise with the harmonics, because harmonics is can be also reduced by other means. You can put filters, you can do control algorithm to eliminate some of the harmonics. So harmonic elimination, there are other options, but winding factor is you cannot increase once you have designed it, right? So that's the limit.
Okay, thank you.
Good questions. Thank you. Maybe you will find some more questions later. Now let's go to the more advanced design process. So far what we have described is a conventional design process, okay? And to do this type of design, actually you need to have quite a lot of experience. So a novice machine designer could find it very difficult, because you have to determine what is magnetic loading acceptable, what is current loading acceptable, what is the dimensions that can be manufactured. All these things only comes from experience, okay? Somebody new, novice person, if we follow that, is very difficult to get the optimum machine. You can still design a machine, but we cannot guarantee it's going to be the best. It can give us the best performance. So then on top of that, now we are designing motors for very challenging applications, such as the EV or electric aircraft or even wind generator for direct drive. So in those type of applications, again, using that design process, conventional design process is not going to work. So what we do now is actually you first find out what is the requirement from the application. So as we have seen in our first lecture, the EV specification determined by the energy department in US, let's say. So that's the requirement for a traction motor. And you can start from there now in this design process. Or your wind generator application may have certain requirement, and you can start from that requirement if you're designing a generator for wind energy. And then all these machines are always going to be run with the power electronics converters. So we can then figure out what are the two machine and converter requirement. And then converter designers can do the design process, and they can also feed back to the application requirement. And then they may tell us that, okay, some of the requirement need to be changed because otherwise you will get a very poor converter. So that feedbacks is there, feedback loop is there. In conventional design, this was not even there, okay? So the next one is, once we have the machine requirement, we then decide the topology. So this part is somewhat similar as the conventional one. Then we do the modeling analysis and FE modeling basically here. And then FE gives you very accurate prediction of the performance. So you then evaluate that performance. That could include electromagnetic performance, thermal, mechanical, or all together as a multi-physics. And then we see whether this performance does satisfy our application or not. If not, then we go back and do this flow chart in a feedback, okay, again and again. So this could be done manually, this loop. That is obviously a lot of time consuming thing if you have to keep doing this again and again for iteration. But this process could be automated as well by the optimization method. So we'll discuss optimization in a later part, maybe in day 5. But today we will just simply discuss this, basically this part, how to do this FE simulation. What does the FE simulation actually does and what it can predict, okay? So finite element, it is actually not just for electromagnetics. It can be used for even civil engineering, mechanical engineering, whoever needs to solve partial differential equations, okay? For electromagnetics or for electric machines, it becomes the partial differential equations solver, and that partial differential equation is Maxwell's equations, okay? So that's what the finite element does in the machine design. It solves Maxwell equations behind the scenes. And if we recall quickly, this is the Maxwell equations of magnetics. The curl of H is the current density and curl of B is 0. Now, usually in the electric machine, this electric field density D, this change of electric field density D doesn't need to be considered. So we can, this part can be neglected when we are doing our electromagnetic analysis or Maxwell's equation solving. So that simply becomes curl of H, solution of curl of H and div of B. So, and then B, if you recall from the fundamental, the flux density B is actually can be also found by taking the curl of the magnetic potential. So in fact, in many finite element analysis, they try to solve this magnetic potential, in fact, so that these are all partial differential equations. So they will solve it in, and then you can find the magnetic potential in, if it is a Cartesian coordinate, you can find the component x, y, z for flux density, b, x, by, bz. And then from there, you can calculate out the radial flux density as well, because conversion from Cartesian coordinate to radial coordinate can easily be done. And if our current is AC, then that becomes in fact a transient type finite element analysis. And in that case, we have to consider the variation of time as well in our quantities, okay? I'm not going through the maths too much. You will have this material available to you, so you can have a look at them later. So that when we have time stepping or transient FE analysis, that it can handle AC current as well as it can handle the rotation of the magnet or the rotor, okay? So there's two ways of doing it, the inclusion of AC current. Either we make our magnetic potential a function of time, or we can handle it like a phasor, okay? So J omega, omega means the frequency of your AC supply. So that, then that again, you can see it's a partial differential equation, whether this or this, both of them are partial differential equation, and it will solve it behind the scene. But when it does this, how can it make it accurate is that it divides the study domain into smaller elements. That's why it's called finite element actually. So you divide the study area or domain into smaller elements, and then you solve those equations in these elements, each of these elements, and then find what's the value of B or what's the value of A in X direction, Y direction, or Z direction, and so on. So these elements could be two-dimensional, three-dimensional. So if we have a 3D finite element model, then the elements could be three-dimensional, hexagon or a tetrahedron, and geometry of this will play a part when you are, and you try to solve those equations in these nodes actually, okay? And if it's a two-dimensional, then it could be a first order triangle or second order triangle. The difference between these two is that you could have more nodes in your triangle, second order triangle, and you'll solve those equations in these points, in fact, okay? And then try to find what is B or what is A at each of these nodes. So that second order obviously will give you more accurate than first order. The good thing is that most of the commercially available finite element software, you just need to select what is the how accurate meshing you want, and then it does for you all the things. It will select whatever the element gives the best accuracy, and accordingly it will mesh your study domain or divide it into the smaller elements, which is the terminology used in FE is meshing. It's called mesh. So you are seeing here an example, a triangular element, and then each node, how it calculates the potentials, okay? And in fact, it becomes a quite complex matrix as well, because it does the solutions in matrix and then add them up. So that the maths behind it is quite complex. So if someone wants to develop that finite element software or want to work in finite element software like companies, then you have to know all this. But if you are just a user, then you may not need to know what's happening behind the scene in the solver. So as you can see, it has to solve so many small elements, a partial differential equation in so many small elements. It's definitely very, very time consuming. So how to reduce the time? There is actually quite elegant way to do it, especially in electric machines, because in electric machines, we have symmetry. Okay, so if we have 4 poles, each pole is identical to one another. So when we do finite element analysis, we don't have to build a full motor. We can simply build the one pole, okay? Or sometimes they even do half a pole, okay? Sometimes even half of the pole is sufficient. So we build just either half of the pole or just one pole. And under one pole, whatever is there, we include that. This is the slot per pole. So for example, in this particular geometry, it's a IPM geometry, flat magnet IPM geometry. So under that, we have 6 slots. And out of these 6 slots, 2 slots will be for each phase. And we will first one could be our A positive phase. Next 2 could be the negative C phase, and these 2 could be the positive B phase, and this could be our A minus. So this, how the phase are distributed in the slots is actually quite easy to determine, because the 3 phase need to be 120 degree apart physically. So that's already tells us what should be the each phase in these slots. And so that's done. And then we, if we know that our dimensions, we can, as you can see, it's not a very difficult geometry. It could be easily drawn if we know the diameters, if we know the width and the height of our slots. So can be done. And that's what part of the FE's analysis actually. The first part is to draw the geometry with the base parameter, the dimensions that you have calculated using the sizing equation. Okay, so you already know most of the major dimensions of this geometry, and then you simply draw it in the first part of your software interface. And so when we do, as we do only the 1/4, if it is a 4-pole machine, or whatever, like if you have 8-pole machine, you will be doing 1/8 of the machine only. So that reduces your time also for the calculation, because our study domain is only 1/4 or 1/8. However, when we do that, we have to define boundaries of our study domain. And these boundary conditions, these boundaries are actually, again, comes from boundary value problem of partial differential equations. Some of you may remember it. So in a machine, usually the outer diameter is a Dirichlet boundary, which basically means that we define the potential, magnetic potential here to be 0. Okay, so that flux doesn't go out of it. Flux is always inside this domain. And same, the center is a Dirichlet boundary, that means 0 potential. The other 2 sides are called the interconnection boundary. This type of boundary actually defines the periodicity, because this is going to repeat. Okay, if we have 4 poles, this structure going to repeat 4 times. So the 2 boundaries, in fact, tell the software or the solver that this is whatever you are solving here is going to repeat in the next whatever number of poles we have. So it only solves this and then it duplicates it. So ultimately, we get the result for the full geometry, although it solved only for 1/4. So that's how it reduces the time. And often there are quite a lot of other things to be considered, such as like if you want to calculate eddy current loss, then those equations need to be able to handle that, the eddy current loss calculation from those flux density and the potentials. And when we do the rotation of the, or when we simulate the rotation of the rotor in finite element, as I mentioned earlier, the time step. So that again, a elegant way is there, which reduces computational time. This is again quite standard in most of the commercially available finite element software. So what they do is your only rotor part going to rotate, right? And then your stator is stationary. And when it rotates, no shape change can occur because that's what the physically, right? When your rotor rotates, no physical shape change happens. So that's what we also need to get in our finite element. So how to do that? Because in this case, we are only moving as part of a geometry, right? So clever way is the air gap actually divided into 3 sections. And in the 3 sections, the top part is assigned as the stator part, bottom part is assigned as the rotor part, and the middle one is actually the air gap. Although actually all 3 are part of the air gap, actual air gap, but the calculation only happens in the middle portion, in which they allow or they can modify the mesh element when the rotor moves, but not the part which is connected to the stator or the bottom part which is connected to the rotor part. So the mesh of those 2 parts remains unchanged when the rotor movement of the rotor is simulated in the finite element. But we may need that when we want to calculate back EMF, because magnet must move, only then you will see the flux change, and then only you will get the EMF calculation from your flux density. So that's why that when we do this rotational simulation of the rotation in the MATLAB, in the finite element, it's referred as a transient finite element because it is now handling that change of flux with time. Also, if we have AC current, then also it is need to handle the change of the quantity with respect to time. Sometimes in some finite element analysis, in fact, allows you to connect the model, the finite element model, to a circuit representation of the input. Okay, so current input to your coil can be represented by current sources like a circuit. The coil here is actually your phase A, phase B, and phase C. And these are the representation of the inductance of your winding, and this will have a link also to the geometry that you have created. Okay? And again, this happens actually this interface happens actually behind the scene, but we can draw this kind of a circuit, and then we can assign this coil A, B, C to the slots. Okay. In some softwares, in some FE softwares, what they do is that you don't need to define a circuit like this. Everything happens in the geometry. So they just provide you an input box in which you can include your current. You can include number of turns. You can even also include any that leakage inductance, which is in the your Z direction, if you are using a two-dimensional finite element. So that if you are doing two-dimensional finite element, we are not looking at what's happening in the axial length, right? And that's acceptable because it is exactly same things going to happen, but in extended length. So two-dimensional model, it gives you good, accurate enough result, except that it cannot account for any leakage flux that is happening in the that Z direction, such as the end windings coming out from the slots, goes through the axial lengths, and then turns back to go to the next slots. Okay, so when it turns back, that part is called end winding. And if we have two dimensions, we are not be able to see what's happening there. Okay, that when the winding turns back from at the back side, and that there is usually some leakage happens, and that gives us an end inductance. So this end inductance cannot be accounted for in a two-dimensional finite element, but it can be included if we do a circuit type of outside circuit interface for the FE geometry. Also, even we can, instead of putting this three-phase current source, we can even put also an inverter here, inverter model here if we want. You can even have the controllers there. So we can elaborate if we would like to do that way. So the motor model is your FE model, but then circuit, controller, etc. could sit in another interface, and both of them can, in many software, both of them can be coupled together. So your controllers runs in the one platform and your FE runs in the other platform, but you at the end you get the performance results out from the FE. So for to show you an example, so the same IPMSM geometry we're seeing here. So that geometry will be built. We assign various material once the geometry built. Magnet material, rotor and stator will be steel material. Windings will have copper in them. And then these shaft and the flux barriers are non-magnetic. So they can be represented just like a air, okay? Or any non-magnetic material we can select. And then we give command to the FE software, which will build a mesh for us. We can ask it to be very precise or very dense in the area where we want more accuracy. So usually the action happens here in the air gap. So we want that part to be densely meshed compared to the yoke. Here, nothing much happens, just the flux goes and then come back. So that's why the meshing here is usually much more dense. So if you want to know more about what's happening in a magnet, maybe you can do also the magnets meshing more dense, and they can be done in the software by selecting certain settings. And once that's done, you ask it to be solved by the solver, and it takes some time depending on how complex your geometry is, what you are asking it to solve for. So, and then when it is done, it will tell you, and then you can go to the post-processing of the result. So what can you see in the result? You can see how the flux lines crossing from your magnet to the stator. You can look at the flux density, whether there is any saturation in your machine, where was the saturation happening, what's the value, is it allowed value or not? All those can be checked in the color plot like this. Then you can also plot the air gap flux density. They usually allow you plotting. So here you can see the flux density of a surface type, air gap flux density of a surface type, and IPM machine calculated by the FE software. You can see that they are ideally we want a sinusoidal waveform right here, but they are not sinusoidal, you can see, and they have this notch here. This notch are due to the slots, because slot part is actually air, right? Air or copper, which has the permeability of copper is also like air. So this part is still, but that part is like air. So that's the effect you see. So where we have still, we have high flux density, but where we have the slot, that means air part, it drops. So that effect of slot can be seen very clearly and nicely in finite element. But if we do analytical calculation, this is very difficult. There are equations to do it, but quite complex to calculate these waveforms analytically. And then if you move your rotor, you can also find the back EMF waveform from the whether it is sinusoidal or not. And then if you have built your machine later after having a quite after optimization or whatever you have done, and then when you are sure that that's the machine you want to build, it can be constructed as a prototype. And then if you do measurement, usually from my experience, the back EMF, measured back EMF and finite element back EMF comes very, very close. Okay, that means FE is very accurate to give you flux density as well as the back EMF waveform. You can also calculate torque. How is the torque induced in the machine? I haven't shown that picture, but can be found. And torque is also quite accurate, especially the average value. And you can also find power if you want to. So all this can be verified if we build the machine, that the measured value and the finite element predicted value are very close. So that's why finite element has become so popular among electrics machine designer, because it can give very, very accurate prediction of the performance of the machine. It is not too good at finding iron losses, because the iron loss model is not accurate. The model that what is in the literature, okay? So we are yet to find the most accurate enough model to calculate iron loss. So finite element doesn't actually, means it always underestimate when it predicts iron loss. So that's the only one which we could not be certain, but for many other very important performance, finite element can give you very, very great results. So that brings us to the end of these 2 hours lectures. In summary, you have learned sizing equation, and that could be used to find the key dimensions. But then we can use some analytical equations to calculate performance, which we haven't discussed here, but in the literature they are available. However, most of those analytical calculations cannot handle magnetic saturation, leakage, flux, or iron loss calculations. So, and they're also not very good at when the geometry is complex. So then the alternative is finite element. They gives you very accurate prediction, but of course they are computationally heavy and could take long time to process, especially if you're optimizing. They have to do this geometry maybe for 100 times or 200 times. So it could take even 24 hours sometimes, especially if it is like, if you are looking at not just electromagnetics, but thermal, mechanical, all if you are processing, it could take even 2 to 3 days sometimes if it is very complex. You maybe Dr. Chu will tell you when he was optimizing, sometimes his optimization ran for days. So that means it is, and you need a quite powerful computer to do that. The workstation is sufficient. You do not need a supercomputer, but you definitely need a very good computer and takes time. So that's the disadvantage for finite element. Okay, so that brings us to the end of this 2 hours lecture. Any question?
Madam, excellent discussion. And we believe our participants, including me, will be, this will be very beneficial. Madam, one point I would like to know that PMSG, permanent magnet synchronous generator, what could be the maximum capacity? Capacity in terms of say megawatt,
okay,
or kilowatt.
All right. So commercially at this stage, they have built a 5 megawatt direct drive permanent magnet generator already by Siemens. Okay. So that is what has been achieved so far.
Actually, one the largest wind turbine that is being installed in Netherlands, that is Halide X, which is of 12 capacity. So the question was in my mind whether that single generator would be able to take care of that.
Perhaps not. So some of the, so because if you go for direct drive, as we have discussed previously, the generators could become extremely large. Yes. Right, so that's why sometimes especially for very large wind generators, the solution is that we go for smaller gear. Okay, one stage gear instead of having 3-4 stage gear. You go for a smaller small stage gear, but you make the generator speed a little bit higher so that you can compromise on the size and also weight. Like you can imagine even a 5 or 6 megawatt generator, how heavy it is, and then you have to put it on the top of the tower. So it's a mammoth task. Yeah, so that's why the challenge is whether we can build generators which is lighter, which is smaller, but can give you the same output power.
Thank you, ma'am.
Thanks, Dulal. Any other questions? All right. So
if you have any question, you can ask Madam if you have any doubt.
All right. So Himanshu has one question: how to work on the software. So in the tutorial, Dr. Chu will show you. At least I'll demonstrate you how that software works. Like I think step by step, he's going to show you. And he may also give you some reference where means you can get access to the free source software, FEsoft software, which are free to download, and some of the things are quite similar. So we use ANSYS Maxwell now, but previously we used another software. It's called at that time it's called Maxsoft from France, CDRET Maxsoft. So some of the geometry or figures that you have seen is actually from Maxsoft CDRET, but recent times we have actually migrated to the ANSYS Maxwell. This is the FE software license at our university, so we migrated to that. And it is a massive software, ANSYS. It doesn't include only electromagnetics. It also allows, or it also have a platform for civil engineering, mechanical engineering, and all others, whoever uses finite element analysis. So electromagnetic part is only a small part, but because it is used by so many other fields, so this is expensive. I think even academic license is relatively expensive. It's something like MATLAB. Like MATLAB is actually expensive software. But as I said, there are free source softwares which you may be able to download, and maybe Dr. Shu will talk about it during the tutorial. Okay. Anything else? Any other questions from anyone?
Yeah. So is there any other question from participant side? We have the tutorial session after lunch. I hope, there will be demonstration, right, madam?
Yes.
So those who have some doubts about the software, they should join, and they should have a flavor of the software, and whatever madam is saying that demo version or the basic version is available, you can try or you can work with that one.
Yep.
So
you
so
can have the step-by-step demonstration in the tutorial. So hopefully those who are interested, it will be useful.
Yeah, so you join from the starting instant, so that you don't miss any of the steps. If you have no question, we can stop here. For this lecture session before the lunch. And if you still have questions, you are always welcome with your questions in the next lecture session. You can put note down your questions, or you can note down your query or doubt, and madam is always there. So thank you, Professor Doctor, for your nice presentation and very informative and useful session. So thank you very much. So we should stop. Right,
yeah,
madam?
let's stop.
Yes.
Yeah, let's stop,
So,
and then we'll
thank
come back
you,
in.
madam.
What time tutorial starting?
Yeah, it is, madam, 1:30 p.m. Indian Standard Time, and Australia AEDT 7 p.m.
Yep, sure. Thank you. Thanks. All right,
So,
then. See you.
Thank you very much,
madam.
Silchar sir.
Whether we'll start after 1 hour?
You tell me whatever as you like. We will do whatever you like.
Okay. So after 1 hour means 1:45.
Which is like for us it will be 7:15. That's okay. 15 minutes later.
Okay.
Yeah, 7:15.
Yeah,
so
7:15.
thank you, madam. Thank you, Tapan, for enquiring. Okay.
Thank you. And please send the Zoom link for the afternoon session.
Yes. Just now I shall send.
Okay. Thank you.
Okay.
Thank you then. See you.
See you, madam. Okay.
Bye.
Thank you, Tapan.
Yeah. Welcome, sir.
Okay, all participants, please wait. I have to take one screenshot. Switch on your camera, please. Madam also, please. So one screenshot is required for attendance. Okay, okay. So you take it. Okay. No problem. Yeah, give me. What happened? Okay, thank you. Thank you. After 1 hour, we'll start our session. Okay.
Yeah, thank you, Zaiki, sir.
Okay, thank you, Dokun. What is it? Save कहाँ कर करें? Stop कर देता हूँ. Stop recording.